All right, so I got the go-ahead that the recording is probably started by now, so I am ready to get going. I'm Michael Peterman. Welcome to LinuxFest Northwest, second day in the morning. Hopefully you guys drank less than I did last night. But I'm here, I made it. That's a win for me right now. But anyway, this talk is about encryption, and it's a fairly kind of a basic introduction, if you will. I go over quite a bit, but hopefully it's something that you'll find interesting and get something out of. So I've been a software engineer for about 15 years. Just real quick about kind of a little bit about me. I did work on digital rights management and digital media delivery for about the first half of my career. So I've got a decent amount of experience working directly with encryption and actually trying to write secure systems that people can't break. So without further ado, we've got our agenda here. I don't think I mentioned this before, but all the slides are encrypted. So it's really going to be a problem later. No, seriously though. Basically, I'll talk a little bit about me real quick, a little introduction, and then we'll get into some of the cryptographic ciphers. We'll talk about symmetric encryption, asymmetric encryption, and then kind of how we actually use this stuff every day. It's kind of all over our lives right now, but my goal is really that you guys take away something about knowing a little bit more about how encryption works, and that there's more of us who know more about it in the future, right? I mean, we need to all learn about this. It's becoming part of our everyday lives. It's not new by any stretch of the imagination, right? But I still see things like this or hear things like this either around the office or when talking to other people about it. And obviously none of these things are remotely true. We don't encrypt things with base64 because that's not encryption. You don't protect public keys, that's why they're called public, and we don't decrypt hashes because they're designed not to work that way. So encryption's been around for a really long time. This is a skytail, I believe is the correct pronunciation, and this is something used by the ancient Greeks and Spartans. It's basically a piece of parchment or leather wrapped around a rod. And if you have a rod of similar size, you can rewrap it again and get the message back out. It's not rocket science. And in fact, it's probably not particularly good because with a whole bunch of different sticks, you could probably find the right size eventually and decrypt it. But this stuff's been around for a really long time. But to talk about it, I think we probably could use some new words, right? So I'll use the word crypto system, which is basically a system that's capable of encrypting and decrypting content. And that content is usually called plain text to begin with and ciphertext once it's encrypted. The ciphertext is the part that you're not supposed to be able to read. And then we have things like a codebook, and a codebook is more like a lookup. So if you have certain symbols of data or chunks of data might be represented as an individual code, we call that a codebook. Cryptanalysis is the science of finding weaknesses in crypto systems and encryption. And then a hash is a one-way function. So I think we probably all know what a hash is. But so simple ciphers, right? The notes or the agenda from earlier was, quote, encrypted with ROT13. And this is very much like a Caesar cipher. And that was actually named after Julius Caesar, who used that to obscure text in anything that was written. Now, whether that was actually effective or not is kind of questionable because it turns out a lot of people back then were wholly illiterate. So encrypting that content, you may have just been able to write it down, and that probably would have been sufficient. But either way, so ROT13 is just a rotation, right? All it does is say take these letters, offset them by 13 mod 26, and you're good to go. And so there's actually a formula for this that's pretty clear. Sorry about the math. There's not a lot of formulas in the whole presentation, but and it actually works, right? It makes the text so that you can't really read it. When I put the agenda up at first, I'm guessing none of you could actually read it. But it has some problems, right? It's not really particularly safe. It's pretty commonly known. And if we take a look at the letters, there's a few of them that show up kind of frequently, right? There's a lot of R's in there. And we actually get into a bit of a problem. It turns out that we can guess what the R is because E comes up a lot, and it translates to R. So just looking at analysis of what letters and letter frequency analysis, you can actually kind of reverse how the encryption works. Again, that works really well for things like the Caesar cipher, simple ciphers like that are just translations. It doesn't work for modern day mathematical-based ciphers. So at some point, we must have gotten better, right? We must have advanced past just the simple substitution ciphers into something that actually works quite a bit better. And this really started to get good kind of in the early 1900s, right? The Room 40 in 1914 was something from the British Army where they captured a bunch of data, German communications, and then later were actually able to decipher them. We actually stockpiled a lot of this information for a long time, and then were able to later use codebooks they discovered from the Germans to actually decrypt their messages. Gilbert Vernon invented the kind of polyalphabetic telegraph. And polyalphabetic, well, a large word, really means that instead of just saying, oh, we'll just shift it by 13 or shift it by 5 in the alphabet, we use different alphabets so that frequency analysis doesn't work anymore, right? Because now E doesn't just turn into R. It turns into R sometimes, but other times it turns into a different letter. And then this is actually a picture of an Enigma machine, which is kind of a typewriter, if you will, type device that has rotors on it and encodes text as you type. And these were, this stuff is actually getting closer to cryptography that actually works, and crypto systems that actually work, that are hard to break. Claude Shannon, around 1945, is kind of generally accepted to be the father of modern mathematical cryptography. His work was cited by DiffieHellman when they were doing the public key crypto systems. And he has his maxim, which is actually kind of a restatement of Kirchhoff's principle, which is that a crypto system should be secure even if everything about it is known. And that's really one of the key things about security for us, is that we assume that everybody knows what you're doing and it's still safe, right? That's one of the key goals. If things are based on obscurity or secrets, they tend not to last. So for real, in 1973, this actually got some standards behind it, right? And so the US government and NIST asked for cipher proposals to actually create an encryption standard. And they got a number of proposals and chose IBM's Lucifer Cipher, which became known as DES, or the Data Encryption Standard. Standards certainly help. They help us get to the point where everybody is using the same type of encryption. It gets wide audience and eyes on it. Generally a very good thing. So when Lucifer was chosen, there was some things that were changed about the algorithm from the initial design from IBM, right? They were convinced to use a slightly smaller key size and that was actually sufficient. And there were changes made to the S box, which is actually a substitution table. Think of it as a giant array where we'd look up a value and translate it into another value. And the algorithm, and that was done by these guys. Does anybody know what building this is, by the way?
NSA.
Yeah, it's the NSA. It's the NSA headquarters in Maryland. And when you kind of read that, you might think later, boy, that seems odd. I feel like they should be, kind of making tweaks to the encryption algorithms that we have. It sounds a little bit scary. And so, is that evil or legit? It appears as though they actually intentionally designed these new tweaks to the algorithms to actually make them safer, which is a good thing in a way. So I guess you could say that it seems legit. But at the same time, there's a little bit about that that's bothersome because they were defending against attacks that the academic community didn't find out about until 20 years later. And they didn't really say anything about it, right? So yes, they made the algorithm better, but they also kind of hid something that they knew that no one else got to know for a while. So we have a new standard now that we generally all use, AES, which was it was a competition held by NIST to find the replacement for DES. DES was old, and this is around 2000, 2001. And this is actually kind of an interesting process. They went through and chose, narrowed it down to 5 algorithms. And this is a side note, I don't actually have a source for this, but supposedly when they did that, they asked each one of the entrants to rank which algorithm they thought was best. And of course, they all chose their own first. Makes sense, right? Who wouldn't? But interestingly enough, Rindall, which is the algorithm that won out and is now known as AES, they all chose second, which I think actually is very telling in that, yeah, of course you choose yours first, but the odds that we would actually have consensus on which one was second best across the board seems to really point to the fact that it really was a well-designed algorithm. Bruce Schneier, a pretty well-known, pretty vocal security analyst, So he had nothing but good things to say about the process that NIST ran in developing AES and the contest they ran to actually choose the new algorithm. So all of these are symmetric ciphers, right? They take in content, apply key, and output ciphertext. It's generally how we picture encryption working, right? Looks pretty easy. But specifically, they're block ciphers, right? They operate on chunks of data at a time. There are different modes for block ciphers. So let's pretend we have this guy, which is just a picture. There's not much to it. And so we want to protect it. Let's encrypt it, right? That worked pretty well, didn't it? No one has any idea what that is. Right? It is totally encrypted, 100%. No. What? Really? Yeah, we ran into this problem again. So we did in fact encrypt the image. That was an encrypted version of that same image. The problem is that we encrypted it using a block cipher mode that will turn all black things and all colors black into the same encrypted value. And so we end up with the same kind of frequency analysis problem where things just got translated, but it didn't really happen correctly. So the model that was used, the mode that was used to encrypt that is called electronic codebook. An electronic codebook looks about like this. We're going to take some plain text, we're going to apply a key, and we're going to get ciphertext out the other end. Now the problem is that if we take the same plain text a few times, we get the same ciphertext out the other side. So, okay, how do we fix this? And by the way, as a side note, the Jeff Atwood, the blogger for Coding Horror, refers to this as encryption mode.fail. Because it clearly did not work. So let's fix this, right? Let's use a different encryption method. And there's, by the way, I'm not going to go over all of them. I'm going to touch on electronic codebook and then CBC, which is cipher block chaining. And in this mode, we take the output of the first encryption block and apply it to the input of the next encryption block. So we get this chaining together, and so there's some sort of feedback that causes noise in the stream. Even if the plain text is the same, the encrypted block from the previous encryption will cause it to not appear the same. Does it look encrypted yet?
Yes.
Yeah, much better. So it's not safe to say, I use AES, without saying what mode I use it in and what I'm trying to do. There are reasons you might want to use the ECB mode, the codebook mode, right? It has a nice feature, which is that you can grab any block in the middle of the file and decrypt it. The problem with this is you actually need to start at the very beginning to get that cipher block chaining all the way to the point that you want to do your decryption. So depending on your use case, you might have different things you need to do, but you have to be mindful of how the encryption is being used, how it's being configured, or else you'll end up with the other tux, and that guy just didn't work at all. So how do we share data, right? This encryption looks pretty easy, right? So if I want to send some encrypted data to you, all I'm going to do is I'm going to encrypt it and send it to you, and then I'll send you the key, an email, something. That's not going to work. I'll encrypt the key and then send you that, and then I'll send you the other key. No, that's not going to work either, right? We get into this problem where I don't really have a way to send this data around to different people. I don't have a way to give you a key. I mean, I could do this 8 or 9 times, but at the end of the day, I still have to give somebody a key to be able to decrypt the key, to decrypt the key, to decrypt the data. So that's why we have public and private key crypto. And this allows the classic characters Alice and Bob, which are very frequently used in cryptography talk, to encrypt and decrypt data and share data without sharing their secret keys. So in this case, they would share their public keys, and Bob can encrypt data that Bob wants to send Alice with Alice's public key, and Alice can read it with her private key, all without exposing that private key that allows reading the data. So this is actually also the foundation of key exchange, which is used at the beginning of every, say, HTTPS transaction. So when you start, when you browse a secure website, right, we start out and we use the keys together to derive a shared secret, just by sharing public keys. There's actually a lot more to it than this, but I don't particularly think I want to put you to sleep with a full DiffieHellman key exchange.
It's so cool, though.
It is. It's another funny thing. Somebody the other day at work said, "Oh yeah, you know DiffieHellman's broken," and I was like, "What?" And it turns out that it is, if you're the NSA and you have those kinds of resources, right? It is actually theoretically broken. The practicality of that exploit is you need a lot of money and a lot of time. So.
Today.
And it turns out, today. Well, it turns out the NSA has both. So, I just assume, in general, and I'm not an anti-government conspiracy theorist of any kind, but I just assume they have all my data already, and that makes my life a lot more comfortable. So I don't have to worry about it anymore. So, yeah, I'm not saying that makes it okay. It just makes me okay with it, which is not the same thing. So hashing. Hashing's pretty clear, and like I said, I think, if you've downloaded a Linux ISO and made sure that it's legit, you've probably gone through this process. And so here's some hashes for this image. And these 3 hashes are cryptographic hashes. I mean, I don't know that I'd necessarily trust MD5 that much anymore. It's pretty small, pretty broken, and if the thing you hash is less than 8 bytes, I'm pretty sure you can just put it into Google and it'll reverse it for you. It's pretty well a solved problem. So, using stronger hashes like SHA-1, SHA-256 are pretty good. There are also other types of hashes like Murmur, and I can't remember another off the top of my head, that are designed more for speed than they are for cryptographic security. So, again, it's a case of knowing what you're trying to do. If you need this to be strong and not ever possibly reversible, then choosing a cryptographic hash will work well for you. But if you need it for performance and you're just trying to get, distill down a unique value out of a piece of data, things like Murmur work very, very well and are much, much more performant. How do we use all this stuff? Very carefully. He does not look like he was very careful. And that's actually, it's exceedingly hard to get right? Using encryption is one thing. Actually writing this stuff, or even writing secure systems around it, is really, really difficult. I worked at a DRM company for a while, and they're well defunct, so I have no problem saying this stuff. But we did a lot of optimizations in a lot of code that we had, and we had the reference implementation for the blowfish algorithm, and we did a lot of optimizations on it, and we were not very good at CI and CD, so we didn't really test, let's say, every build. And we found out eventually that we had actually changed the blowfish algorithm to be what we affectionately started referring to as lockfish, because the name of the company started with the word lock. We kind of messed it up, right? And the problem is that as soon as you get into that realm, I don't know what the security of this new lockfish algorithm is, right? We knew what blowfish was. We knew it was fairly well tested. So doing this is very, very hard. To be clear, these optimizations were made by people who were extremely smart, right? These guys had done lots of optimizations into, say, the Dolby AAC encoder with no problems at all. Just kind of messed up the encryption algorithm a little bit. So in hindsight, I think that's the kind of thing you should never do. But at the time, I don't know, it all seemed legit. So realistically, what do we do with this stuff? Passwords, we usually use hashes. Symmetrically encrypt sensitive data, right? We want to keep things safe, so we use symmetric encryption. It's pretty fast. It does a good job. And we use public key cryptography to share sensitive data. A lot of times what you're sharing is actually a symmetric key. So you might use public key cryptography to protect a key to open up something that's symmetrically encrypted, which is actually exactly how SSL works as well, right? Or HTTPS, TLS, right? It sets up a session and then shares a key, and then once you're actually sending data back and forth, the payloads are all symmetrically encrypted. It's a performance thing. It's much, much faster than asymmetric or public key cryptography. So writing crypto yourself, just don't. It's really a bad idea. Messing with it, not really a good idea. I mean, there are enough libraries out there today. Taking on the extra dependency to have it done right is definitely worth it. It's actually about all I have. Do you guys have any questions? Yeah.
So is this all a moot point now if we have quantum computers, or?
I don't know. I don't have one. The question is if this is a moot point if we have quantum computers. I don't know, honestly. I think that it's possible that huge jump in performance would allow things to be broken that just aren't possible today. But again, especially if you look at things like the exploit that's available against the DiffieHellman key exchange algorithm, right? That requires massive amounts of computing power, and it's still not actually breaking the algorithm. It's exploiting an implementation flaw, right? It's that we chose kind of these prime numbers, but we only really use a few of them instead of deriving a lot of them. So I think it might change how we look at things, but I don't know if it's going to completely destroy it. Yes?
One of the key things I've seen done wrong is people will take like the NIST standards, see the prime numbers, and say, oh, I'll just use that prime number. How do you get people to use it correctly and understand that they have to generate their own prime numbers at times?
Yeah, so the question is about, people taking maybe the standards that are written by NIST and reusing them. By the way, I'm re-saying the questions because there's a microphone here, and in the future, just weird to talk about the future now, people may actually want to be able to understand what the question was, not just the answer. Yeah, I don't know. It's very hard, right? I mean, getting people to understand that you can't just copy and paste the examples in a world where a lot of code is copy and pasted directly from sites like Stack Overflow or wherever you find it on the internet, a GitHub gist, then I don't have a good answer to that, right? It's a problem, and actually that's I believe where the DiffieHellman exploit comes from, is that we copied and pasted, we reused things that we shouldn't have. Ideally it comes from better libraries, better solid implementations of this stuff, rather than people re-implementing it, right? Take on the dependency for the solid implementation as opposed to doing it yourself. And that has to have enforcement in it that it will require you to have new primes, however that works, I don't know, but something like that would actually get us to a better place, I think. Yeah.
Well, this is still on topic, but suppose you've got a database, MySQL,
Mm-hmm.
and you use AES encryption that's built into it.
Mm-hmm.
Then you have PHP application. You don't know what to do with the key.
Yeah.
So you embed it in the code, obfuscate the code. Does any of that give you any security whatsoever?
So you're in an interesting problem space, right? Because you're kind of outside where cryptography will exactly help you when it comes to protecting the secret. If you think about the Kirchhoff's principle or Shannon's maxim, depending on which one you prefer to use, if you assume everybody knows everything about what you're doing, then protecting a key that's written in the code is not really very helpful, right? If somebody gains access to the server, they certainly can get the key. Obfuscating the code maybe makes it take another 5-10 minutes. Turns out bad guys have borderline infinite amounts of free time. Which, by the way, I cannot relate to or understand, but they do. They don't sleep. I don't know. I picture people in the basement in my head, but whatever. I think you've taken steps, but really that last mile of getting that key into the code is the hard part. Encrypting the data and having it at rest encrypted, that's great. But protecting that key is extremely hard without doing something like every time the server comes up, I go seed it with the key, right? And at that point, yeah, you're back in the, even if they know everything I'm doing, it's still pretty darn hard.
I hate doing this, but I'm giving a talk on that topic next session.
Awesome. He's giving a talk on that topic next session. I just knew that.
The password management one.
CC 115.
Yeah.
Which was?
CC 115. Yeah.
Okay.
Yeah, it's a legitimate hard problem. In fact, we've tried to find solutions to this pretty much every place that I've worked, and they've ranged from, we have a service that runs on every server that we seed with the key when the server comes up, to we just gave up and we put it in the files. It really runs the gamut. And trying to find industry best practices for this kind of yields a big mess. There aren't a lot of them. There aren't a lot of people that solve it really, really well. It's a hard problem. Yeah.
Best practices?
I'm sorry?
I've always heard the phrase best practices used as code word for popular ones.
Yeah. The question is, or comment is that best practices are more popular practices than best. And I think you're right. Presumably they're popular for a reason. But doing the diligence to find out why they're popular is probably a really good idea. Kind of like copying and pasting that code off of Stack Overflow. That doesn't make it right. It just means it's on the internet. Anything else? Well, thank you guys very much.